Okay, so let me recall the main principal constructions. We have reduced a deformation quantization problem at least a problem of finding deformation quantization to the problem of finding a Markov-Cartan element in the in the differential graded algebra of polydifferential operators. So this Lie algebra is denoted by d poly of M. It consists of multi-differential operators of polydifferential operators, and the grading is given by the number of arguments of these operators, and also the differential is given by the Horseshoe differential and the Lie bracket is just a Gerstenhaber bracket. So finding a star product which is associative is equivalent to finding an element B equal to I think it begins with H bar. Just let me recall it. Yeah, H bar. A by 2 plus some H square. Sorry, HK times PK in D poly 2 of M augmented by adding the formal variable H bar, which verifies the Markov-Cartan equation. So this is associative if and only if delta B plus 1/2 of B commuting with B is equal to 0. That was the first thing. Second, I said that Markov-Cartan equations, elements of Markov-Cartan equations, go well with the higher homotopy algebras. I'm going to explain this today, but first I recall the definitions I gave of L-infinity algebras, or more properly, probably, of homology. I think it is called homotopy Lie, high homotopy Lie algebras. So high homotopy Lie algebras, so L-infinity algebras, are graded vector spaces equipped with a map with a map denoted by L. L is a co-derivation of degree 1 on the exterior algebra or exterior coalgebra generated by the shift of V. So this is, we regard these exterior powers as the co-free coalgebra, co-generated by the shift v dot of 1, v dot sub v dot 1. So this map should be from lambda star of v to lambda star of v dot 1. And the only condition we have is that first L is, actually there are two conditions. So the first one I already spoke about. It is that L is a co-derivation of the coalgebra. So does everybody understand what it means to be a co-derivation? So if you, once again, if you look at the definition of derivations of an algebra, then the only algebraic property that it should verify, it is a linear map which verifies the only algebraic property. It verifies Leibniz rule. So dually, co-derivation should verify a co-Leibniz rule. So it is the rule which you obtain by dualizing the usual Leibniz rule. So let me recall that Leibniz rule is x of product A times B is equal to x AB plus AXB. Sometimes instead of plus, you need to write minus because of the grading. And co-Leibniz rule is dual notion. Here you have a co-multiplication from C to C and the C. So it sends some element A into A sub 1 times the A sub B sub 2, sorry, A sub 1, A sub 2. Here I have some summation sign suppressed because, of course, not every element in tensor product of vector space has this form. It is only decomposable. Only decomposable elements have this form. Well, in these terms, you have the following identity: L of A1 tensor L of A2 is equal to L of A1 tensor A2 plus A1 tensor L of A2. As you see, on the left, we have the result of co-multiplication applied to L of A. And on the right, we have kind of Leibniz rule applied, where we apply L to the tensor product A1 tensor A2. So this is the first condition. And the second condition is even more evident. It is that L squared should be equal to 0. So this is the shortest way to define L infinity structure. However, not probably the most convincing or the most satisfying, I would say, because of course everybody wants to have some more or less hand-on treatment, hand-on treatment of some abstract notions. And as far as this hand-on treatment is concerned, every L infinity structure is determined by the collection of its scalar coefficients. So let me recall that since lambda of V is actually a co-free coalgebra, then every co-derivation of this coalgebra is uniquely determined by the restriction onto the sub the restriction, I can say determined by co-restriction of L onto V, onto the cogenerator set. So co-restriction is kind of projection onto the cogenerator set. So here we should use this kind of composition, projection of L onto V, where we insert V into its exterior power as the first power, and its exterior algebra as the first power. So when we take this projection, it gives us a map from lambda dot of V. I'm omitting the shift for the sake of brevity into V. Since this is just the direct sum of lambda k, lambda n of V for n greater or equal to 0, again greater or equal to 1, probably better to begin with 1. Yeah. Then this restriction, this projection, is actually uniquely determined by the maps Ln from lambda n V onto V. So it's just a composition of inclusion into lambda dot V, then taking L of this sort into of V, and then taking the projection. So this is Ln, and this Ln, I told you, they verify certain algebraic relations. So these relations are easily seen as follows. So the first three of them, at least. So the first relation is very easy. It is just L1 square is equal to 0. So it means that actually L1 determines a co-chain differential in V. Yeah, of course, lambda L1 is just a map from V to V of degree 1. Sorry, deg Ln, yes, in general is 2 minus n, so deg L1 is equal to 1, right? So that's the first relation. The second relation is that L1 verifies, I'm cutting the edges, so I'm making shortcuts everywhere. So L1 should verify the Leibniz rule, the graded Leibniz rule, with respect to L2, which is the map from the exterior square of V into V of degree 0. So L2 plays the role of a lead bracket, and L1 verifies Leibniz rule. That is collectively, if you take both L1 and L2, you obtain a structure which resembles very much the differential graded Lie algebra structure, except for one condition which should be verified for differential graded Lie algebras. This condition is that L2 should verify the Jacobi identity. And the third identity, the third relation which we have, takes care of this Jacobi identity. Actually, it gives that if you take differential of L3, so when I say differential of a map, we shall use this notion today, and we have a map from one chain complex to another chain complex. Let me write this way. So consider the space of all homomorphisms from one chain complex, linear homomorphisms, from one chain complex to another chain complex, right? It is just linear homomorphism. They can change the degree of elements, of homogeneous elements. So we shall assume that F is a homomorphism here of degree, say, K. This K can be either positive or negative. Then differential of f is a map which, when applied to some c, small c in C capital, is equal to d of f of c minus 1 to the power k f of dc. So probably I should put parentheses here like this. So in general, so now it is clear what it means. I have d of L3. D of L3 is a map, and this map should be equal to the what they call Jacobi-eta of L2. Yeah, let me write it down as Jacobi-eta. So it's kind of L2 of A, B, C minus plus or minus L2 of B, C, A plus or minus L2 of C, A, B. And here, of course, D is just the L1 differential. So it means that even though L2 need not verify the Jacobi identity on the nose, still on the level of cohomology, L2 induces a well-defined bracket which verifies Jacobi identity, or rather say the graded Jacobi identity. And that is the defect of L2 of the Jacobi identity of L2 is taken care of by the map L3. Yeah, the map L3 is, as you can clearly see, the map from lambda 3 of V into V of degree -1. I hope all this is more or less clear now. So let me proceed with the example. Some particular example of infinity algebra, important but particular example, is every differential graded Lie algebra. You just take L1 equal to D, differential of this algebra, and L2 equal to the bracket. And then since the bracket verifies Jacobi identity, we can take L3 and all the other high degree maps L4, L5, and so on equal to 0. With this data now, the differential graded Lie algebra G is L infinity algebra. Now, the definition of L infinity map comes very naturally in these terms. In the terms which I use this term to define the L infinity algebra, and the same terms work very well to define the L infinity morphisms or L infinity homomorphisms. So L infinity homomorphism between two L infinity algebras B and B, say, and W, say, is a map F from one co-free coalgebra co-generated by V dot shifted into another co-free coalgebra co-generated by W dot shifted. And this F should verify two conditions as well. F is a homomorphism of coalgebras. That is to say, in those terms which I used at the first slide, we have the following identity. When you apply delta to F of some C, what you obtain is actually F of C1 times F of C2, and this should be equal to F of C1 tensor F of C2. So F should be homomorphism of coalgebras, and also F should commute with the structure maps. So if LV and LW are the structure maps of the corresponding L infinity algebras, we should have this identity. And now, as before, since everything is free here, the F is determined, map F, the map is determined by its by a composition of F with projection onto W. So in this case, it gives us a series of maps, just as before, Fn from lambda n V into W. And this Fn should verify certain conditions, which are pretty lengthy and a little bit awkward to write down, except for the first couple of them. So the first condition is pretty simple. F1 should commute with L1 in the sense that F1 of L1 comma V is equal to L1 comma W composed with F1. So F1 is a cochain map. And the second condition is also something you can pretty easily expect. It is that F1 interacts in a pretty nice manner with the structure maps, with the brackets. So the brackets are given by L2 map. So we have the following identity: F1 of bracket, that is of L2 of AB. I am omitting V and W from now on because it actually makes very little sense when it is clear what is on what side, but it will make our writing a little bit shorter. So when we take this composition F1 of L2 of AB and subtract L2 of F1 of A, F1 of V, we shall obtain something which is governed by the second element in the row. That is, we have D F2 of A, B. So F2, so it says that even though F1 can fail to be a homomorphism of Lie algebras, but on the level of cohomology, it actually gives a homomorphism, because the difference between these two elements, this difference is just a condition that F1 is a homomorphism. This difference between these two maps is given by a boundary, by a coboundary. The coboundary is induced by F2. So, but F2 is, I mean, let's put it shortly. So let's say F2 fixes this on cohomology, in cohomology. Of course, this D is again this differential induced by D in V and W. So this D is differential in L2 of, sorry, it's a differential in the mapping space from L2, lambda 2 of V into W. Okay. So here we have this condition, and of course, if F from a Lie algebra differential graded Lie algebra into differential graded Lie coalgebra, Lie algebra H, is a homomorphism of differential graded Lie algebra, then of course it is L infinity homomorphisms again. So everything is matched, and we just put F2 and F3 and everything beyond that to be equal to 0. However, the contrary is not true. The contrary is not true. It's not true. If G and H are two differential graded Lie algebras, and one can define a genuine L infinity morphism between them. So this F capital, a map from G dot into H dot, L infinity, if it is given by a set of maps Fn is a map from lambda n of G into H, and the following conditions should be verified. D of Fn applied to A1 to An should be equal to the sum of two terms, actually the sum of two sums. The first sum is just given by Fn minus 1 applied to Ai, Aj, comma, A1, I, Aj, An. So plus or minus depending on certain, sign rules, minus the sum over P and Q, which sum up to N. Oh, sorry, to to N. And sum of all unshuffles. We begin with the sign again. Sign depends on sigma and many other things, so I just put tilde to designate this. It doesn't depend only on sigma, it depends also on degrees of the elements. And here we have a bracket of Fp of F sigma of 1, so F sigma of P. Sorry, I forgot to put in parentheses. And FQ of remaining. I'm putting dots here. And I think I also need 1/2 here just to take care of repeating indices. Okay, so this is the definition. And to make sure that this notion is important and that this is not just some pure game of imagination, I'm going to prove the following theorem. So we begin with some definition. So let's put part 3 of my talk. Definition. So the purpose of allowing these L infinity morphisms between two differential graded Lie algebras rather than just sticking to the homomorphisms of Lie algebras is the following. Definition: a homomorphism of Lie algebras F from G to H is called quasi-isomorphism. Quasi, I don't know how to pronounce this. Quasi, probably. Isomorphism. If F induces an isomorphism in cohomology. And the theorem which I'm going to prove is the following. for every quasi-isomorphism. So we stick to the definition, so everything in our case, in our situation, is over characteristic zero field, most probably over R or C, or maybe over Q, but everything is over characteristic zero field to avoid all difficulties. So okay, so for every quasi-isomorphism, F, there exists G, an L infinity map from H to G, such that the composition of G and F and F and G are homotopic to identity. I'm going to sketch the proof of this map, of this claim, and I'm going to be pretty sketchy. I'm sorry for this. So what I'm doing, I'll assume that actually the map G into H is an inclusion. And hence there should be an inverse projection G1 from H into F is a projection inverse to F. It's not totally inverse. If it is just inverse, it would be not a projection, it would be just an isomorphism. Then there would be no problem. However, I say projection, I mean it is left inverse of F. That is to say, G1 composed with F. Sorry. Let me see. Left to right. Just a little confused. So, what should be what? We want to. So not left, right. I'm sorry. Should be not left. It should be right. Right, inverse of F. So what I do, sorry, of course it should be into G. Okay, so just try to. So I'm just to take care of one of this. So I don't want to prove both compositions. That would be a little bit too much. I want to prove just one of them. So I want to make the second, the opposite composition as simple as possible. So let me see. What do we have? What do we have here? We have yeah, I think it is like this. Okay, anything. So it's a good projection. So F, I think F G1 should be identity of H. That's what I assume. Okay. So probably it should be projection. Actually, it should be inclusion. That's probably better. Phrases. Inclusion. Okay, now I'm going to construct the inverse. So this helps us when we prove the inverse map. Okay, that the inverse is good. Otherwise, we should have to take care of to construct some series of homotopy maps. I don't know, probably not. Just I don't know. Okay. So we have this, an inverse G1 composed with F is not identity, but it is identity is homotopic to identity. So it should be identity of G plus some homotopy, one composed with H1, sorry, decomposed with H1 plus H1 composed with D. So we have this series of assumptions. And we also assume that H1 verifies the Leibniz rule with respect to the bracket in G. So these three conditions makes the situation rather special, but the fact is that in spite of being pretty special, so the third condition is the Leibniz rule condition, in spite of being pretty special, this situation is rather general. In fact, everything can be decomposed into a series of compositions of maps with this property. To see the existence of such maps, you can use some kind of linear algebra argument, because you see, the only thing we have to take care of when we construct G1, for instance, is that the map F induces an isomorphism in cohomology. So we can actually find convenient basis in G and H, such that this isomorphism in homotopy, in homology, will make part of the map F. So we choose basis such that homology is already inside G and inside H. Then I put F to be, we will see that F is as an isomorphism between the elements of this basis, and then I add additional maps, additional projections and everything for G1 to extend F, to extend this inverse on the level of homology to a map, to a linear map from H to G. So G1 is just a linear map which verifies these two conditions. Okay, now let's go on. Unfortunately, G1 need not verify the homomorphity condition. Need not be homomorphism, actually, need not be homomorphism. So it means that G1 composed with the bracket of A and B need not be equal to the bracket of G1 of A with G1 of B. It should be equal to some map phi of A and B. Now, if you take the differential of the map phi, then you see that, so what is it? It is just d of phi of A, B minus with certain sign, which I don't want to take care of, plus or minus, that is of phi of dA, comma B, plus minus phi of A dB. right? So if you now apply G to both parts of this equality, you will see that G1 commutes with differential, and the bracket verifies the Leibniz rule with respect to the differential. So this should vanish. So phi is a closed element in the complex of homomorphisms between the chain complexes. Yeah. So phi is an element of lambda 2 of G into, sorry, I think it is inverse, right? Yeah, it is inverse. Lambda 2 of H to lambda to G, and it commutes with the differential. Hence, it induces a map in homology, sorry. So homology of lambda 2 of H into homology of G. Right. So when I apply phi to an element in homology, we apply it, say, to some x. So I'll denote this map induced by phi lower star of x and y. So every element x and y, they are in the image of F1. So they're F1 of some alpha, of F1 of some beta, right? Very nice. So when we apply G1, and of course alpha and beta are closed, right? So when we apply G1 of of F1 of alpha, F1 of beta, what do we have? You see, I replace this element here. So when I want to, sorry, not this element, let me see, this element here. When I replace L and B by elements in homology, I actually can replace these elements in homology by representatives, right? So when I if x and y are representatives of the homology class, what do we have here? So when I apply it here, what I have, well, first of all, F1 is a homomorphism. So F1 can be taken outside of the bracket. So I have G1 of of A1 of F1. Sorry, not F1, just F. I forgot to say that. Of course, I don't have F1, I have just F. G1 of F of the bracket, alpha and beta. So what I have, it is just the bracket alpha and beta plus this dH1 plus H1D, but H1D vanishes because D of alpha and beta is equal to 0. So we have D of H1 of alpha beta. Then I have also minus, when I substitute it here, what I have is just minus alpha plus D of H1 of alpha, beta plus D of H1 of beta, right? So when I open all the brackets, I'll see that alpha commutes with beta vanishes, and the remaining part will look like d of h1 of alpha beta plus minus h1 of d of h1 of alpha beta minus alpha dh1 of beta, and eventually also have the last but not the least term, which looks like plus minus dh1 alpha dh1 beta. So the first thing we see it is that on the level of cohomology, this map phi star should vanish, because this difference phi star phi of f alpha f of beta consists of exact elements. This element is clearly exact. This element is exact because d of beta is equal to 0. This element is exact for the same reason, and this is clearly exact. So it is closed, and hence we can take, so since there exists, so since this element vanishes on the level of cohomology, it is not just, it is a trivial element of cohomology, and as such, it should be equal to a co-boundary. So there should exist G2 map from lambda 2 of H into G, such that D of G2 is equal to phi. If you look here, we shall see that it is precisely the condition for the an infinity map. And this, moreover, if we look at this identity here, we shall see that G2 is actually given by this identity. G2 is equal to H1 of alpha beta minus, let me put it like this here, G2 of alpha beta minus H1 of alpha beta minus alpha H1 of beta. So this, but however, this for alpha and beta closed of the form F. Sorry, I think I need to put it like this. Not here, not of the form, but something like this. If you take f of alpha, f of beta, alpha beta closed, then you have this identity, plus commutator of the form, sorry, plus d. Now, if you look at the last term here, you see it actually looks like d of H1 of alpha d let me, sorry, just, I think I need to put it like this, sorry. Let me rewrite it on the next page. So last term looked like this. it looks like D of H1 alpha, D H1 beta, right? However, here it is equal to D of 1/2 H1. Okay, sorry. I need to put it like this: 1/2 of H1 of alpha, D of H1 of beta, plus or minus D of H1 of alpha, H1 of beta. Right? I think it is like this, right? So what I claim it is that the remaining part looks like D of some H2. If you look at this formula and you remember what is G2, it is something. So this element was in the formula for phi of F of alpha, F of beta. And it is equal to D G2 of F of alpha, F of beta, right? And yeah, so if we write down the formula for G2, we shall see that the remaining part will look like a closed element. Not an exact element. Now, if we remember that H1 verifies the Leibniz rule, we shall see that actually the first three terms actually vanish. They cancel out. And in this case, G2 of F of alpha, F of beta is equal to D of H2 of alpha beta for some H2. So it is not just exact, not just close, it is exact, which is very important. So now we go forward and we consider the map psi, for instance, of A, B, and C. It is equal to the difference G2 of A, B, C plus minus G2 of B, C, A plus minus and so on. So we just take these kind of elements. This is the if you look at the definition of an infinity map, it is just this part of this map, this part of the identity. And we subtract the remaining part, and it's just G2 of AB, comma F, G1, sorry, G1 of C, and so on. The remaining part is just given by the same cyclic permutation. Then again, D of psi is equal to 0, and there exists a well-defined psi star. Hence, we can apply psi star to x, y, and z in a homology of H, and as such they are equal to f of certain alpha, f of certain beta, and z and f of certain gamma, right? So we again have to look at psi of f of alpha, f of beta, f of gamma, and if you substitute this formula, this which we have just observed here, into the formula, into the definition of G, right? In the definition of everything, we shall see that what we have on the right will look like a closed element, D of something, right? So this is actually what something will look like H3 of alpha, beta, gamma. So it means that on the level of homology, psi star is equal to 0. And hence they exist G3 such that D G3 is equal to psi, and this gives us the next step. And also we shall have not only G3 but also this map H3. If we go on like this, go on and on like this, and at every step we shall get Gn and Hn. We find this condition, and when we get come to the infinity, we get all the remaining terms for the L infinity map. So as you see, we get the inverse map just by repeating this exercise on and on. Okay, that is the purpose of having this relaxing these definitions of homomorphism to L infinity morphisms. And for us, the main purpose is given by the following theorem. Suppose phi is a Marikatan element of G, and f from G to H is an infinity map. Then the following element, capital Pi, equal to the sum 1 over k factorial fn, fk pi, comma, sorry, not pi, phi, comma phi, is again a Marikatan element, but in G, in H. This is very simple, actually, a simple exercise, but let me prove this. Again, a little bit sketchy, but still. We just consider the differential of pi. It is given by sum 1 over k factorial. Well, yeah, I mean, this formula, of course, assumes that this right-hand side converges in some sense. So this convergence condition is usually verified on the nose by some certain filtration or something. In particular, in our case, since we can introduce this formal variable h bar, and this will provide the condition we need. So whatever, we just assume that this convergence is not a problem. The convergence is assumed. And proceed with our computations. 1 over k of d of fk of phi, comma phi, comma phi. So I omit all the signs and just skip all the signs because it is really too hard to take care of them unless you read something in the paper. But on the blackboard, even on the whiteboard like this, it is almost impossible to follow, to trace all the signs. But believe me, it is possible. It is doable. So we have 1 over k factorial. D of fk, you know, it is equal to differential of fk applied to phi, comma phi, comma phi, plus or minus, I don't care. Fk applied to differential applied to every element inside, but all the elements inside are the same. So what you actually obtain, just k copies of the same element, fk d phi, comma phi, comma phi, comma phi. Right? So that's the first term. So that's the second term. The first term is actually equal to the differential of fk. And if we look at this definition here, we can now replace differential of fk by this composition. There will be two terms. So the first term will look like fk minus 1 applied to phi, comma phi, phi, phi. And I mean, there should be as many elements, as many possibilities to choose 2 copies of phi from this row there are. And as you know, there should be precisely the binomial coefficient k over 2 to do so. Different ways to do so. And there also be 1/2 of f, 1/2 sum over all permutations over all on shuffles fp of phi, comma phi, comma phi, fq of phi, comma phi, comma phi. There should be as many elements of this sort, as many different ways to unshuffle this line of phi's there are. And they exactly as many as the binomial coefficient p over n, right? So n over p, or p plus q over p, right? Now, it's almost evident that what we have here will cancel out this element. Let me hint this briefly because we're running out of time. I want to end a little bit earlier today because tomorrow I have to leave for Novosibirsk early in the morning. So this element and this element will actually cancel out because d phi plus 1/2 phi phi is equal to 0. Phi is a Maurer-Cartan element, right? So these 2 elements will cancel out because of the Maurer-Cartan identity. You can see that even the coefficients match because k over k factorial is a k1 over k minus 1 factorial. And then we also have k times k minus 1 divided by 2 here, right? And number of elements inside will be equal to k minus 1. So just to match this, we need to take fk plus 2. So it will give us k plus 1 times k over 2 divided by k plus 1 factorial. And as you see, it's precisely 1 over k factorial, 1/2 times over k minus 1 factorial. So these two elements now cancel due to this Maurer-Cartan identity, right? And the remaining part is equal precisely to 1/2 of pi comma pi, because the coefficients 1/k factorial will couple to give us binomial coefficients here, precisely what we need. Okay, now so what we have proved it is that up to the sign, which I totally omit, we have d pi plus 1/2 pi pi equal to 0. That's precisely Maurer-Cartan element, Maurer-Cartan equation. That's all. Okay. I think this is more or less the end for today. Our next purpose is to prove the theorem that actually, in the situation which we considered before, and I recall you that we had two differential graded Lie algebras. One algebra is algebra of polyvector fields with 0 differential and with its Houghton bracket. And the other algebra is the algebra of polydifferential operators with Horseshoe differential and with Gersten-Haber bracket. We shall show that these two algebras are in fact quasi-isomorphic as differential graded Lie algebras. In the sense that what we know already that they exist a map chi, the Horseshoe constant Rosenberg map, which does not commute with the brackets. And so it is not quasi-isomorphism on the nose. That's the problem. But it induces isomorphism cohomology. So what we're going to prove, it is that chi can be completed, can be extended to certain L-infinity map, which we should denote by U, L-infinity map, from left to right. And see, and so applying U to the bivector pi, which, as you know, is a Maurer-Cartan element on the left. So this is G for us. We obtain Maurer-Cartan on the right. Now, and that will solve the deformation quantization problem completely. Well, up to the equivalence and so on, but I'll probably skip this for first reading. And that's what we're going to do next time. Just before we proceed, before I say goodbye today, let me observe that Horseshoe constant Rosenberg theorem, which I formulated at the first lecture this semester, says that the Horseshoe constant Rosenberg map induces isomorphism cohomology, isomorphism of Lie algebras. Even though it doesn't commute with the bracket itself. It induces isomorphism cohomology. So the left-hand side is actually the cohomology of the right-hand side. And when a Lie algebra is differential graded Lie algebra is quasi-isomorphic to its cohomology, it's called formal. And that's why this theorem is called Kontsevich formality theorem. So next time I'm going to sketch the proof of this theorem. And when this next time will take place, either on the 8th of March online or on the 15th of March offline, then it is for you to choose. Okay, that's all for today. If you have questions, please ask.
Thank you very much.
You're welcome. Any other questions? If not, then I stop the recording. And I stop the recording.